Okay, so let's start. We talked about cache memory. We talked about cache memory in my video that I recorded, and hopefully you have seen that because we are going to do some practice problems today. So in cache memory part 2, we talked about direct mapping. What's the difference between direct mapping? What's the difference between fully associative mapping and also set associative? So typically in the current cache that we see, we would see that the cache uses set associative mapping. So the difference between direct mapping, fully associative, and set associative is obviously in the memory address that is used to map the block memory to the cache. Am I audible? I'm audible, right? And I'm recording, okay. So for example, direct mapping, we have the main memory address like so. We have tag over here, and we have line, and then we have word. Now here it specifies that the tag is 8 bits, the line is 14 bits, and also the word is 2 bits. But in reality, this depends on your memory size, your main memory size, and also your cache size. So based on those sizes, your main memory address will change. So it depends, because you can have variations of memory or variations of size of memory, variations of size of cache. Therefore, your main memory address will correspond to that as well. Okay, so please watch my video if you haven't on this one. And then we have an equation to talk about direct mapping, whereby we can know what is the cache line number it is mapped onto by using cache line number equals to main memory block address modulo number of lines in the cache. Modulo means that you divide it, and then whatever that is the remainder, that will be the cache line number. Okay. And then we also talked about how the direct mapping cache organization is, what goes first. You first looked at the line number, and then you go for the tag, and then from then on, you find the word that you actually want. So I also talked about this one. And then we talked about this example as well. And then we had this summary, and we need to remember this to do our practice problem in a bit. Okay, so here, this is an example for direct mapping. So given the main memory size of 4 gigabytes, cache size of 1 megabyte, and also block size of 4 kilobyte, the word size of 1 byte. Okay, so let's first look at this guy over here. We see that this is the direct mapping memory address. This is the format. Okay, whereby we have the tag, we have the line number, and we have the block or line offset. The block or line offset is where you would store your words or where you would store your data. The line number is the line number in the cache. You have your cache. Your cache is divided into cache lines, and each cache line is represented by a cache line number. And then you have your main memory. This is your cache. Your cache line goes from up to down, and then you have your main memory. Your main memory is divided into blocks. You call them blocks. Your cache, you call them line. You want to map your main memory block onto your line. That is why we need the mapping, which is the direct, the fully associative, and also the set associative. Why? Because cache has a smaller number of size compared to main memory, of course, because cache is supposed to be fast. When you have something, when you have a memory that is fast, it means that the capacity is going to be smaller. And if you have something that is very big, it is most likely to be slower. So the main memory is going to be slower than the cache, and the cache helps to bridge the mismatch in speed between the CPU and the main memory, because the main memory is slow. So the cache acts like the fast memory to bridge that mismatch. Okay, so when you look at processes, they would advertise what is the L1, what is the L2, and what is the L3. Typically, you would look at the L3. The bigger the L3, you say, oh, this is better. So that was this is what the cache is. It tells you how fast your cache is going to be. Okay. So for back to this example, we know that for direct mapping, the format should be tag, and then we have the line number, and we also have the data associated with this guy, which is also called the block offset, or we can also call this as the line offset. Sorry for the bad handwriting. So this is the format for direct mapping. You will see in the coming slides that fully associative and set associative have a different format for the main memory address. So you have to remember the format for each. Okay, so back to this question. Now it's asking us, find the memory address bits split. When they ask you like this, something like this, the split, which means that you first need to know what is the total size of the memory address in bits. How many bits is assigned as the memory address. And then from the total number of bits, how many bits are assigned as the tag, how many bits are assigned as the line number, and how many bits are assigned as the block offset or line offset. So that is what it means when they ask you memory address bit split. And then when they ask you about tag directory size, we are talking about this guy, but not entirely. We're talking about this tag, but since we have a lot of tags inside our memory, inside our cache, we would have to multiply it by the number of cache lines because the tag is associated to the cache. If you don't know this, it means that you haven't watched my video. So please watch that. Okay, so let's start with this A example. So first off, we know that the main memory size is 4 GB. So to translate that in log of 2 or in this form, I break 4 into 2 to the 2, which is just 4, and then I times it with 2 to the 30. How do I know gigabyte corresponds to 2 to the 30? Am I muting you guys? No, okay. So basically there's a formula. So if it is kilobyte, it is 2 to the 10 bytes. If it is megabyte, it is 2 to the 20 byte. And then if it is, what comes after mega? Giga. If it's gigabyte, and then you would have 2 to the 30 byte, and so on. So you go from kilo, mega, giga, what comes after giga? I don't remember actually. So it follows that. Okay, so this is supposed to be a K, but it's very ugly. Okay, that's kilobyte for you. Okay, so this is the formula that you can try to remember. So I look at this 4 GB, I can immediately convert it into the 2 to the power of something, right? So 4 is 2 to the 2, and gigabyte is going to be 2 to the 30. So 2 to the 2 times with 2 to the 30, basic math, this would become 2 to the 32 because you're basically adding 2 and 30 together. So you would get your 2 to the 30 bytes. And then your block size is 4 kilobyte. 4 kilobyte. So 2 to the 2 as well, times with 2 to the 10 byte. So you would get 2 to the 12 byte. And then I want to know how many blocks are there in the main memory. Okay, so before we go for that, let me try to refresh your mind. But I know a lot of you have not seen the video. So let's see. Let me teach you this that you have not seen yet. So the main memory over here, we know that it is 4 GB, right? Okay. 4 GB. I'm recording. Okay. Why is my caption saying Spark Gabby? Okay, never mind that. 4 GB for the main memory, and then we have the cache size of 1 megabyte. My face is blocking this. Okay, 1 megabyte. And I told you just now that your main memory is divided into blocks. Okay, so we have a lot of blocks. We don't know what the size of each block is yet. Oh, we do. It's in the question. The block size is 4 kilobyte. So to know the total number of blocks for the main memory, I would have to divide the main memory size divided by the size of one block, right? To get the total number of blocks. So this is what I'm trying to do. 2 to the 32 divided by 2 to the 12 would give me 2 to the 20. So 2 to the 20 is the number of blocks that is in the memory. So that is a lot of blocks. Now, these 2 to the 20 number of blocks will be mapped onto the cache. One block will be mapped onto one cache line. So the cache is divided into lines. The cache is divided into lines called the cache lines. So here we are not informed of the size of one cache line. So this is what we need to find. But we have a hint over here. If we know the block size, we can actually know what is the line size. If we know the block size, we will know what is the line size. So let me write that somewhere. Block size will be equal to line size. Okay, is everyone following me so far? Everyone okay?
Yes, doctor.
Okay. So we already know that the line size is supposed to be 4 kilobyte as well, because it should be the same. Okay, so back to this calculation over here, we found out that the main memory size is 2 to the 32 byte, right? And then we found out that the block size is 4 kilobyte. And then from there, we found out the number of blocks in the main memory. Now, I put here 2 to the 32 byte, and I set over here 32 bits of memory address. When I have this size, I need 32 bits to make my memory. I need 32 bits to make my memory for the entire memory, main memory. So I would know that the format of my memory address will be 32 bits. Based off the main memory address, I convert it to 2 to the power of something. That 2 to the power of something is going to be the number of bits for my memory address format. Okay, doesn't seem very straightforward, but this is how it is. Okay, so now that I know that it is 2 to the 32, I know, okay, the physical address bit or the main memory address bit is going to be 32 bits. Now I need to split this 32 bits into the tag, the line, and also the block offset that I told you earlier over here, the format of the direct mapping memory address. Okay. So what other information that we have? We have the number of blocks in the main memory. So that means that this block numbering will go from 0 up until 2 to the 20 number of blocks. So this is the information that I have so far. Okay, so moving on. I need to use a different color. Okay, orange. So back to this. Now that we are trying to find the word size, okay, we have this information. We have not done anything yet to this information. So 1 megabyte is equal to 1 times 10 to the 20 byte, which is just 2 to the 20. Now 2 to the 20 is going to be the, sorry, I'm talking about the cache, not the word size. The cache size of 1 megabyte. 1 megabyte is equal to 1 times 10 to the 20 byte. So this is going to be your cache size. And we know that one cache line is equal to the same size of the block. Cache line equals to, sorry, cache line size is equal to block size. So I wrote over here 4 kilobyte for one cache line. Okay, so if I know what the total size of my cache is, which is 1 megabyte, and I know what the size of one cache line is, I will know how many cache lines I have inside my cache. So I would do 2 to the 20 bytes divided by 2 to the 12 byte. Where did I get the 2 to the 12? The 2 to the 12 is from here, 4 kilobyte, which is the size of one cache line. The total cache divided by the size of one cache line would give me the total number of cache lines. So I have 2 to the 8 number of cache lines. Now, to assign a number to each of these cache lines in binary number, to assign a binary number to all of these cache lines, I would need 8 bits. 8 bits, which means that I need like 8 digits of binary number to assign the line number, to assign all of my cache lines. Because I have 2 to the 8 number of cache lines, therefore I need this 8 bits or 8 binary digits to assign the line number. Okay, so what information do I have so far? I have 32 bits of main memory address. This is the first information that we got from the 2 to the 32 4 gigabyte memory address, sorry, main memory. And then we know that the block size is equal to the cache line size. And this was 2 to the 12, which is 12 bits to assign each block offset. And then we have 8 bits to assign the line number. So remember the format for direct mapping. We have tag. That's a A, by the way. And this is our line number. Okay, and then this is going to be our block offset. I don't know what's wrong with my handwriting. Okay, so this is supposed to be a B, block offset. Tag, line number, and block offset. So we know what the cache line size is, which is 12 bits. So this is going to be 12 bits over here. And then, oh, sorry, this is the number of cache line. Sorry. Number of cache line is supposed to be 8 bits, sorry. Okay, block offset is 12 bits. My bad. Okay, so we know that the total size of the main memory address is 32 bits, right? So let me do like that, 32 bits, which means that we already know how many bits is our tag, which is, if my math is mathing, it's supposed to be 20, I think. No, it's 12. So the total is 32 bits. You minus with the 8 bits and minus with the 12 bits. This is 20 in total. So you would get 12 bits as your tag. Okay, 12 bits as your tag. Okay, what else? So we have solved A, memory address bit split. We know that the total is 32. We found out what the line number is. It needs to be addressed by 8 bits because it has 2 to the 8. And then we know that the block offset is just basically the same size as our block size. It says block offset and line offset, by the way. They have this guy has multiple names, by the way. Block offset, line offset. Sometimes they even call it as word. But the most common is block offset and line offset. Let's just keep it at that. Okay. So from there, we know that the tag is 12 bits. Okay. Next, what is the tag directory size? So this is what we have found so far. We found out that the tag bits is 12 bits. That does not answer B. That does not answer B because this is just the tag bits. What is the total bits for the entire cache? We need to find that one because each cache line is associated with a tag. I want to know how many bits are used as tags. Okay, so I think it's in this next slide. So since we know that the tag is 12 bits and 2 to the 8 is the number of cache lines, therefore, the number of tag size, directory size, will be 3072 bits. These are the number of bits that I use as my tag directory. It's like your address book. Okay, so how did I know that the cache line is 2 to the 8? Let's go back. The number of cache lines is supposed to follow Oh, sorry, it was here. We did the cache size divided by 1 cache line size. You would get the number of cache lines, which is 2 to the 8. 2 to the 8 means that you need 8 bits to assign the line number. 12 times, sorry, 2 to the 8. Okay, let me repeat myself over there. Okay, so I told you that I want to find the tag directory size, right? I know that one memory address or one cache line would have a tag size of 12 bits. Now, since I know that my cache line, the total cache lines is 2 to the 8, therefore, I know that each cache line would need a tag of 12 bits. So I would multiply 12 bits with 2 to the 8 total number of cache lines. Therefore, I would have 3072. Okay, so that's your answer for B. Does anyone have any questions about this one? Everyone's okay or just clueless at this point? Okay, so this is recorded.
So far.
So far, so good?
Yeah.
Okay. So this is recorded. If you can't keep up, you can obviously look back at the recording, and you can also text me on WhatsApp if you have any further, you need further clarification on my explanation about this practice problem. But I recommend you to watch the lecture first, because this is very much related to the lecture. Okay, so I also included a nicely typed answer over here if you can't read my handwriting. Then let's go for the next practice problem, which is based on fully associative. Is it fully associative or set associative? Let's see, where is it? It's this one. Okay, so this is our next example, which is based on the fully associative mapping. Now you would see that the question is exactly the same. Given the main memory size of 4 GB, cache size of 1 MB, block size of 4 KB, the same. The difference is in the format. I want you to emphasize on understanding the formatting. This is why I don't want you guys to like have a headache about the math. Let's just use the same math and try to understand the formatting of these different mappings. Okay, so how does the fully associative mapping look like? Let's see. So in my summary over here, we have seen that the associative mapping is, this is the format. We have a block number or a tag, which we can just call this as a tag. And then we have the block or line offset. The block or line offset. Now remember, this is based on the block size, which is also the same as the cache line size. Okay, so this is the same as direct mapping as well. The only difference is in the front part, which is we have a tag. We don't have a line number. So this is the difference between associative and direct mapping. Associative only has a tag to identify each cache line, whereas for direct mapping, you would need both. First, the line number, and then you would need the tag to identify each block or line offset, okay, or cache line. So back to our question. What time is it? Okay. Back to our question, we want to find the memory address bit split. Now we know that the format is going to be divided between tag and also block or line offset. Oops, can't write. I'm just going to write off because it's hard to write. Okay, so 4 GB is going to be 2 to the 2 times 2 to the 30. We have seen this one before. I hope I don't have to explain again. So it's 2 to the 32 byte. Therefore, we know that our memory address has 32 bits. So this is what I wrote over here, 32 bits. So this guy, the total size is 32 bits, even though it doesn't have a line number, like direct mapping, but this is the total size. So you have to work with that. Okay, so we know that the 4 kilobyte corresponds to the block size. Remember, the main memory is divided into blocks. If one block is 4 kilobyte, I would have 2 to the 20 number of blocks in my main memory, which goes from 0 up until 2 to the 20 blocks. This is the number of blocks. Okay. And then to identify each block by a tag, we need at least 20 bits. Now, why do we need 20 bits? Because for the fully associative mapping, each block is only identified using the tag. Previously, we had the line and also the tag. So we had like 2 parameters to differentiate between lines. So the way that they organize things would be slightly different. For fully associative, it would scan through all the tags. No, this is the wrong place to scan. It will scan through all the tags and then see which is the tag that corresponds to the memory address that is required by the CPU. So to do that, they would scan this guy over here, which means that the tag would have to identify each cache line. The tag would have to identify each cache line, if that makes sense. So you would have a lot of tag bits compared to direct mapping. So it's going to be more tag bits compared to direct mapping because this is your entire address over here compared to the direct mapping. The direct mapping, you had like 2, right? You had like the number of house and then you had like the street number. For this guy, everyone is identified by a street number. So you would have to need a lot of street numbers, which is like bizarre. Okay, never mind about that. So therefore, to identify each block by a tag, we need 20 bits, not its. Let me put the B over there. Bits. Okay, we need 20 bits. So if I know that my tag size is 20 bits and this guy is supposed to be 32 bits, therefore I know that my block offset bits is going to be 12 bits. Now, does this correspond to the block size given over here? Let's see. So 4 kilobyte is equal to 2 to the 2 times 2 to the 10. Which gives me 2 to the 12, which means that I would have 12 bits as my block offset or line offset, which is correct. That's one way of checking your work. So that is your memory address bit split. Easy compared to the direct mapping. Okay, so the second one is tag directory size. I believe you have a little bit of understanding on this one. If you know what your tag bits are, you need to multiply by the number of cache line to find your tag directory size. So you need to find out how many cache lines do you have over here. So let's find out. So if I have a cache size of 1 megabyte and I know that one cache line is 2 to the 12 or 4 kilobyte, I can find out what is my total number of cache lines, which is 2 to the 8 over here. 2 to the 20, which is my cache size, divided by the block size or the cache line size, which is 2 to the 12. I would get 2 to the 8 because 20 minus 12. Therefore, my tag directory size is going to be 2 to the 8, which is the total number of cache lines. Okay, this is total number of cache line times with 20 bits that I know, which is the street address for all my data. So I would need 5120 bits of street address to like identify each cache line. Okay. So that is it for your tag directory size. So please expect something similar in your exam, at least for this chapter. Okay. So this is typed 1. If you can't read my handwriting, sometimes I can't myself. So let's go to the part number 3. which is on replacement algorithm. Now, why do we need our replacement algorithm? Let's go back. Let's go do a little recap on that one. Now, some mapping requires replacement algorithm, some does not. For direct mapping, let me go back to the first mapping. First mapping, where are you? Okay, so in direct mapping, please read over here. In direct mapping, there is no need of any replacement algorithm because a main memory block can map only to a particular line of cache. We know what block is, we know what line is. And for direct mapping, there is no choosing. There is no choosing because remember that I told you it has an equation. Yeah, it has to follow that equation. So let's say block 0, it has to be mapped onto cache line 0. I cannot play around. It's not flexible. I have to follow the equation. What equation am I talking about? This equation. This equation, okay? So because it follows this equation, there's no playing around. It's not flexible. Therefore, the replacement algorithm, there's no need for the replacement algorithm because I know exactly how my cache needs to be replaced. I know how my cache needs to be replaced. If it's not there, that's fine. I just ask the main memory, and the main memory, let's say I need the memory from block number 12. So I know block number 12 will be mapped onto the cache line number 12. I don't need an algorithm to decide on that. It's straightforward. An algorithm is needed if it is complicated. If it's not complicated, there's no need for an algorithm. So direct mapping is very straightforward. Therefore, there is no need for the replacement algorithm. Just use the equation to find out what line, cache line number the memory will go to. Okay, so thus the new incoming block will always replace the existing block in that particular line based on the equation. Okay, so that is direct mapping. Now, fully associative mapping, because we know that the format is based solely on tag, then we have the block offset. So the PA split, the PA means physical address or main memory address, doesn't specify a line field number. So when I want to map my memory onto my cache, it is actually flexible. So let me try to draw this. Oh, I already draw it here, but it's very ugly. Let me draw it again. The drawing is by me. If it's going to be ugly, it's going to be ugly again, right? But we'll try. Okay, so this is the main memory, and this is the cache. Okay, let me get rid of this. Okay. Okay, so we know that the main memory is composed of a number of blocks. We have seen that it was 2 to the 20 for the main memory. In our practice problem, this is not always the case, just an example. And then we have seen that our total cache line was 2 to the 8. The cache line is always going to be smaller than the main memory. And this is indicated by small m, and the main memory is indicated by capital M. So small m is 2 to the 8, capital M is 2 to the 20. The block number goes from 0 to 220, 2 to the 20, and the cache line goes from 0 to 2 to the 8. The cache size is always smaller than the main memory as well because it is fast. Okay, now that we got that one out of the way, now let's say I want to map the one of the blocks in the main memory. Let's say I want to go for block number 5. Now, for fully associative cache, the great thing about it is totally flexible in the sense that whichever cache line that is available, it doesn't have any memory there, I can just map it. It can be at the bottom of the cache, it can be at 0, at cache line number 0, it doesn't matter. As long as it is available, the block can map onto that cache line. Now, the bad thing about this is it does not specify any queue. There's no hint as to where it will be mapped. There's no hint. And I also cannot predict where it would be mapped. So this is the downside of fully associative cache. Now, because of that, the way that we want to replace our cache when new memory wants to come in is going to be slightly harder because we don't know which one came first, which is more important because it was mapped randomly. Therefore, we need a replacement algorithm. So this is the basis for replacement algorithm to help us figure out which cache line needs to be replaced, which goes first. I mean, who gets to be replaced first, okay? Now let's go back to replacement algorithm. So once a cache has been filled by a memory that it is, the main memory mapped its data onto this guy. One more thing that I want to tell you guys, when the memory is mapped, when the data is mapped onto the cache, the data is not lost in the main memory. The data is copied into the cache. So don't think that the main memory would lose some size. No, we are copying from the main memory. Nothing is lost. But since cache is volatile, so if I shut down my computer, the cache is going to be gone. The cache memory is going to be gone. So it's going to start new. So this is the function of cache. So once the cache has been filled, when a new block is brought into the cache, one of the existing blocks must be replaced. For direct mapping, there is only one possible line for any particular block and no choice is possible. Therefore, we don't need replacement algorithm. For associative and also set associative technique or mapping, a replacement algorithm is needed. To achieve high speed, an algorithm must be implemented in hardware. So we don't want the decision to replace which cache line to hamper the speed of our machine. So we need a replacement algorithm that is very effective. So we have several approaches to replace our cache line. So this is the 4 most common. I can only find 3. Okay, let me get back to you on this one. So we only have 3 here. 1, 2, 3. So the first one is least recently used, or LRU. You need to remember the abbreviation. So this is the most effective. It replaces the block in the set that has been in the cache longest with no reference to it. So I have my cache lines and all this memory inside my cache. So the cache that is in the cache the longest, which means that it's been there forever, and no one has been calling that cache line. No one has been calling that cache line. Therefore, you would replace that cache line with the new block memory. If the memory has been there for a long time, but it keeps on getting called by the CPU, then this is not the least recently used. You would only replace it if the CPU does not ever call it for the longest time. Okay. And then for the second one, the first in, first out, very straightforward. We use the round robin system. So I have A, B, C, D, E, F. So A came in first into my cache. The memory of A came in first into my cache. Therefore, this A gets out first. So after that comes F. And then B gets replaced because it is the longest here. It gets replaced by G block. And then C is the longest. It was the first in, and then it is replaced by H block memory. First in, first out. Very straightforward. FI, FO. And then we have the third replacement algorithm, which is least frequently used, or LFU. To replace the block in the set that has experienced the fewest references, could be implemented by associating a counter with each line. So this is slightly complex. What it means is that you have your cache lines, and then each cache line has been called several times. So each time it is called, there is a counter over here that keeps track of how many times it has been called. Let's say this guy gets called 8 times. This guy gets called 1 time. And then this cache line gets called 5 times. So I would see, oh, cache line number 2, or no, sorry, this is cache line number 1. This is 0. Cache line number 1 has only been called once. So this guy is the least frequently used. Let's replace this guy with the new block. So that is the third approach. And then apart from the replacement algorithm, we also have to figure out how to write the new block, right? We are not just replacing the cache line with the block memory, we also have to write into the cache. So there are two ways to do this, which is write through and write back. So write through is the simplest technique. All write operations are made to main memory as well as to cache. All write operations are made to main memory as well as to cache. What does that mean? Let's try to imagine a scenario. Okay, so I am the user. Sorry, I can't use the user. We need to say CPU here. Okay, so let's say this is our cache over here, and this is our main memory. Now, I have mapped my data onto the cache. Doesn't matter, direct mapping, set associative, it doesn't matter at this point. I want to know, so the CPU decides that, oh, the memory inside this cache, I want to modify it. I want to write on it. Let's say the cache is divided into like 20 words. The block line offset has 20 words inside it. And the CPU wants to change one out of the 20 words. The 20 words is the data inside the block or line offset. Okay, so I hope everyone is still following me here. So the CPU decides I need to change one word inside of this block line offset. I need to change it. So what happens is that it not only writes in the cache, it also does the same in the main memory. So it would write also in here. I don't know how it's supposed to look like, the writing thing. But if something changes in the cache, it would change in the main memory. Okay, so that is what it means by write through. It's like tembus. What do you call tembus? Through. Okay, so and then we have a write back approach. So this is our first approach for replacing blocks. Second one is to write back. The write back method minimizes memory writes. Updates are made only in the cache, which means that if you are changing anything, you change it in the cache. The CPU changes only the cache. That is supposed to be a P. Don't know. Yeah, I think I need to buy a new digital tablet. Okay, so the CPU writes into the cache, only in the cache. It does not get written through to the main memory because this is the write back approach. And then portions of main memory are therefore become invalid because they are not coherent anymore. They are not coherent anymore. So what you have in the cache is no longer the same in the main memory because the CPU already written something inside the cache, or it has modified something in the cache. So hence accesses by IO modules can be allowed only through cache. Therefore, if we want to access the modified memory, you have to go through the cache. You have to go through the cache. The cache will obviously update the main memory, but it will do this at its own time. Therefore, any access can only be done through the cache, and you can't ever bypass cache to go to the main memory. We have seen this. We have seen this in, let me go back. We have seen this organization before. It was, I told you there was two organizations of the cache. One is the processor has access to the main memory because it can access the system bus. But sometimes the cache is going to be physically interposed between the processor and the main memory. Therefore, any access to the processor needs to be done through the cache and then from the cache to the main memory. So this is the write back approach. If the write through approach, you get rid of this. Whatever the CPU wants to write, it also writes in the main memory. But you would have to write a lot more, right? So that's the disadvantage. It depends on what you want, actually. Okay, so let's go back to our slide over here. Okay, so is that clear, the write through and write back difference? Any questions? Everyone's okay, or are you just asleep? It's very cold today. Okay, so I'm going to continue if there are no questions. Okay, so for the effect of line size, I have already written everything that you need to know. So there are 6 statements that you need to read. The statement number 1 is the larger the block size, the better will be the spatial locality. If you don't know what spatial locality is, go back to the slide, go back to the lecture. What this means, the larger the block size, the better the spatial locality. And we have 2 cases whereby we decrease the block size and what happens if we increase the block size. So please read through that. And then statement number 2, in direct map cache, block size does not affect the cache tag. And there is an explanation on why the cache tag is not affected if your block size changes. You can increase, you can decrease the block size, but your cache tag will not change. Why? So there is this explanation over here. Okay. And then statement number 3, in fully associative cache with decreasing block size, cache tag is reduced and vice versa. Also, I've given you the explanation. I need you guys to read through this because it's basically just reading. If you understand the formatting of each mapping, then it would make sense to you. And then statement number 4, in set associative cache, block size does not affect cache tag. So even if you increase or decrease the block size, the cache tag will remain the same. And then statement number 5, a smaller cache block incurs a lower cache miss penalty. And the last statement, a smaller cache tag ensures a lower cache hit time. And then we also discussed about the multi-level cache, whereby we have seen that the L1 cache was divided into L1D and L1I. This is also in the AMD Ryzen processor, I believe. I think it was 2 L1 multi-levels as well. So the L1 was divided into 2, but the L2 was just a unified cache. Is it this one? Wait. Oh, that's the topic here. So multi-level cache, I believe I have touched on this slightly. We have L1 and then we have L2 and then we have L3. This was in the earlier lectures of this chapter. And then L1 is faster, L2 is, L1 is the fastest, L2 is faster, L3 is the slowest. This was the smallest in capacity. So I'm just going to write this like this. And then bigger capacity, and this is not the right notation. So capacity, this guy would be bigger and this guy would be bigger in capacity. This is capacity. And then in terms of access time, the L1 would be the fastest, L2 would be faster, and L3 would be the slowest based on their size. Now, we have talked about the multi-level cache. There's no surprise over there. What I want to talk about here is the unified versus the split cache. Now, this is a diagram that I have introduced before. We can see that the L1 is divided into 2. This is called a split cache. Even though it is in the same level L1, it is split into 2 because when you split into 2, you are able to divide the function of each cache. So the function for L1D, let's say, is for instruction. And then for the L1I, the main function is to handle the data. So one handles instruction, the other handles data. So when you divide this, you can get it to be faster. You can get it to be faster. And then for your L2, this is called unified cache. And then for your L3, you have your unified cache. But actually your L2 is also divided, but it is divided between cores. So within this core, you have the split, you have the unified and the unified. Within this core, you have the split, the unified L2, the unified L3. Okay. So advantages of split cache is that it eliminates cache contention between instruction, fetch, decode, and execution unit. So you don't have your L1 having a meeting who gets what gets to do, what instruction gets to go first. So when you have that split, they know what they're supposed to do and it becomes faster. And this is very important in pipelining. And then these are some examples of problem with cache, and this is the solution. I want you guys to go through this as well. This one is not so important. And we are done with chapter 4. So I will see you tomorrow. We will start on chapter 5. Okay, so take care, everyone. Have a great rest of the day. For those having exam, all the best. Take care. Bye-bye.
Thank you, Doctor.
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 Welcome. Bye-bye.
Thank you, Doctor.
Thank you, Doctor.
Bye-bye. Welcome.